Should be good now. Cool. So hello, everybody. Thank you for coming to our 15th event. We've had a 3-month hiatus, but we are back now with Pavel Kroupa. I'm very pleased to have him because he is an expert in many different topics in astronomy. To start listing them off, I mean, for stellar populations and cluster formations and multiple star distribution functions and galaxy formation and evolution and nature of gravitation. And so this is why we have him today. He's going to discuss dark matter, or at least the nature of it, and give us a small introduction. So thank you very much, Professor Kroupa. You can share when you are ready.
Okay, thank you. I'm attempting to share now. The screen, yes, I think you can see it, right?
Yes.
Okay, good. So, yeah, the title is chosen to impart the concept that there are some fairly easy things about dark matter, which I hope to convey to you today. And so thank you for asking me to present in this occasion. So let's go into it. First of all, I apologize, I can't cover all the topics I would have liked to touch. I referred to the Golden Webinar in Astrophysics I held on April 9th last year. And also there's this dark matter crisis blog, which you might like to look at if you are interested in this topic. So, as in the Golden Webinar, I'm starting with this, with the two fundamental assumptions which the current standard model of cosmology is based upon. And these two assumptions are that the Einsteinian Newtonian formulation of gravitation is valid everywhere, and that all matter was created in the Big Bang. So these are fairly strong assumptions. Now one then confronts these two assumptions with observations, such as, for example, the cosmic microwave background and galaxy rotation curves. And when doing so, then one finds that 3 additional auxiliary assumptions are required. The one being inflation, dark matter, and dark energy need to be added as additional assumptions to try to make this work. And I should add here that this dark matter can be cold, warm, or fuzzy, or axion. It doesn't really matter, because one has to explain the very large dark matter content of small dwarf galaxies. And so the fuzzy dark matter must be behaving similarly to the cold dark matter, and the same for warm dark matter. So we don't really need to distinguish between these types for the present, in the present context. And so this leads to a model, that's the current standard model of cosmology. There was a Big Bang inflationary period here, then the universe expands. After about 380,000 years, the plasma has sufficiently cooled for to recombine, and so it becomes a neutral here, and then at some point the first structures start, the first stars form, and the universe evolves, and we observe it today with our telescopes, with this epoch of new inflation actually starting, driven by probably dark energy. At least that's the current consensus on this model. The structures forming from the cosmic microwave background here, which is essentially the photosphere of the Big Bang, out to here are possible because the dark matter does not react to electromagnetic forces, and therefore it can start clumping gravitationally well before the normal matter, which is too hot, can do so. In fact, the dark matter can already start clumping even before the recombination. So there's significant need to add this dark matter component to make structure growth possible. So there's an implication of this concerning galaxy rotation curves, which I think is interesting, and which is generally not where astronomers and the public is not so aware of. And that is that according to the Standard Model of Cosmology, galaxies will look as follows. So we have the galaxy, which is surrounded by this huge dark matter halo. So this is about the correct scale. This would be, for example, our Milky Way. We are at about this distance from the center of the Milky Way. And surrounding us is this huge dark matter halo, which is composed of dark matter particles, but also many, many dark matter subhalos which are orbiting within the structure and slowly shrinking due to dynamical friction towards the center and also merging with this central galaxy. So this leads us to a fundamental problem, and that is that 90% of all galaxies are disk galaxies, as we know from observation, but one cannot predict the rotation curve. So you might find this a bit strange because apparently the dark matter, one of the strong arguments for dark matter are the rotation curves, but given the observed matter distribution, such as in this galaxy, it is impossible, truly impossible, to actually predict the rotation curve of such a galaxy. So if you have an exam question in your master's lecture, and that exam question asks you to calculate the rotation curve of a galaxy in which you have the observed mass distribution, you will fail the exam. Yeah? And so here's the problem. So given an observed mass distribution, it is impossible to calculate the circular velocities of stars within it. And so the question is, why can one not do that? And that's very simple. For example, here we have a plot from this paper. This is the mass of the galaxy in stars, and this is the mass of its dark matter halo from the theory. And there is a scatter because each galaxy has its own merger history, own formation history. And so, for example, the Milky Way has a mass of a few times 10 to the 10 solar masses, and it can be in a dark matter halo, which is not quite 10 to the 12 solar masses heavy, or it can be in a dark matter halo which extends to nearly 10 to the 13 solar masses, but we don't know because we can't observe it. Yeah? Furthermore, this dark matter halo can be more or less concentrated. And so, for example, if we look at a dark matter halo of a mass of 10 to the 12 solar masses, it can have this small concentration, that's the scale here, this concentration of the dark matter halo, or it can be much more concentrated, a factor of 10 or more concentrated. And so we don't know about this. So we observe a galaxy, but we don't know what dark matter halo is around it. The dark matter halo can be rotating this way or that way. It'll have these dark matter subhalos, and we can measure this rotation curve. This particular case might have this type of rotation curve. So this is the rotation of the stars and gas going around the center of this galaxy, and this is the distance from the center of the galaxy. So it's rotating, for example, at 40 kilometers per second at a distance of 6 kiloparsecs from the center in this hypothetical example. But then the same galaxy could have a dark matter halo which has this shape, and could have then a rotation curve which goes down because of the way the dark matter is arranged. Or it could have a dark matter halo which is this shape, and then it would have a rotation curve which would be this way because of the way the dark matter halo is arranged. Yeah? So we don't know. It's impossible to calculate or predict the rotation curve from the measured mass distribution of a galaxy. So despite this problem, we do know, of course, that dark matter exists. At least this is what the colleagues are telling us. And it is the central pillar of the Standard Model of Cosmology is that cold or warm dark matter particles must exist. If these particles do not exist, then the Standard Model of Cosmology is dead. Yeah, it's wiped out. And so it's really crucial to find these particles. So this has become a next to religious belief, the fact that they must exist, because otherwise the whole SMoC goes down the drain. And so today everyone basically knows that dark matter is there, and we only need to find it. And so there's been an overwhelming number of dark matter searches since the 1980s. Yeah, so for example, there's Borexino, and then there's Juno, and Kamland, and all these others. So there's this paper you can look at here, which gives a nice discussion of this. And there are many other searches for the dark matter particles on Earth, under the ground, in deep mines, or even using satellites going around the Earth. And nothing has been found at all, despite 40 years of effort. Now that's a fact. But there is a simpler and cheaper method to test if dark matter exists, because the problem with this is that despite not having found anything, we know dark matter exists. It's just not been found yet. So we just have to continue searching. The dark matter particles might have just properties we haven't yet managed to find in the detectors, which are being built everywhere around this planet. Wherever you might look, every country is actually looking for dark matter. And so there is actually a very simple way to test for the existence of dark matter, which again, for some reason, is not really being followed much by the community. And that is just for testing for the existence of dark matter via Chandrasekhar dynamical friction. It's a very cheap, very simple method. And let me explain it to you. So the standard model of cosmology predicts actually a new phenomenon. So if galaxies have these dark matter halos around them, then any other galaxy entering this dark matter halo will suffer Chandrasekhar dynamical friction. So that's a new phenomenon, which is a positive side of that theory. And so we have the situation, we have our galaxy, its dark matter halo, and then this galaxy here enters this dark matter halo and starts orbiting within it. And what happens here in detail is extremely well understood. And that's what's being shown schematically here. So this galaxy enters the dark matter halo of the big galaxy. These are the dark matter particles belonging to the host galaxy. Of course, the particles are also in this dark matter halo, which belong to this galaxy. And so this galaxy is racing through this dark matter halo, and it gravitationally focuses all these dark matter particles behind it. There's a wake of dark matter which builds up. So one can visualize the process by now saying that this wake gravitates back at this galaxy, slowing it down. But this, of course, can be calculated in detail by transfer of momentum. You can see that this particle loses a velocity component in that direction, and that one also. This compensates by slowing this one down. And so by a direct calculation of all these encounters with these myriads of dark matter particles which are passing past, that's what Chandrasekhar did. One gets this deceleration formula. So this is the rate of slowing down of this galaxy per unit time. So the velocity changes, get slower with time according to this equation. So this equation looks a bit complicated, but it depends on the velocity raised to the power of 3, the velocity of this galaxy here. It depends on the mass of this galaxy, and it depends on the dark matter density. How many particles are there? How much mass density is there per unit volume around you? So basically, how much momentum is being transferred from this galaxy to that galaxy. That's what this data is defined here. But note the point here. Interesting is that it's the multiplication between the mass of the dark matter particle and the number density, which means it's the product which matters. And the product is defined by the theory from the Big Bang. That's not a number you can really tune up or down. Yeah, and so this test is insensitive to the mass m of the individual dark matter particle. It can be extremely low mass axions. It can be even primordial black holes, because this product is what is fixed by the theory. And so we have a really beautiful, very robust test for the dark matter particles' existence. And we all know about this process from the solar system. So this is a nice video which shows the launching of the Voyager spacecraft from Earth. It's accelerated by an encounter with Jupiter. That's the slingshot. It's kicked out to a higher velocity and then past Saturn. It's again sped up and then past Uranus, sped up, and then it leaves the solar system at some point. So we cannot launch from this inner part of the solar system out to the edge because it takes too much energy, but we use the planets to accelerate the spacecraft outwards. And this slingshot is exactly what's happening when a galaxy enters the dark matter halo of another galaxy. So imagine that we'd have billions and billions of such spacecraft being constantly launched from Earth, orbiting in the solar system. Then with time, these orbits of the planets would slowly shrink and they would all merge with the sun because these lightweight satellites would be accelerated outwards through all these slingshot encounters with the planets, and the planets lose angular momentum, and they would then just shrink towards the sun and actually ultimately merge with the sun. And so that's exactly the same physics which is happening here. It's completely standard Newtonian dynamics. There's no free parameter which you can turn up or down in this particular game. And so we have the situation: the galaxy enters the dark matter halo of the big galaxy. it slows down because the wake forms, and it slowly spirals down into this galaxy and merges. So, and this is the reason why galaxies merge. This is why every astronomer today, or nearly every astronomer today, thinks that galaxies have this magic property that when they come together, they will merge. It only happens if there is a dark matter halo. Okay, only when there's dark matter. If the dark matter halo is not here, then this galaxy would just happily orbit past and would exit again on a hyperbolic orbit. And so we've applied this test by looking at the orbits of satellite galaxies. And so here's the Fornax dwarf galaxy. That's what it looks like. It has a mass of some 10 to the, I've forgotten the number, 10 to the 5 solar masses, maybe 10 to the 7. Very low mass. It's barely heavier than a globular cluster. It's about 100 times bigger than a globular cluster. And this is the research paper published in 2011, led by Gary Angus, where we looked at 4 satellite galaxies, where we know the distances and the velocity vectors of these galaxies. And the outcome of this study of actually orbiting these backwards, taking into account dynamical friction, is simply put in these words. The Milky Way satellite galaxies, which are 100 to 1,000 times heavier than in stars because of their own dark matter halos, are moving too fast for the distances and ages. Okay, so they are at a given distance, which we measure, and then have a certain velocity, and those don't match together statistically with the fact that they should have these dark matter halos, and our Milky Way should have a dark matter halo. Okay, so this indicates already very strongly that there is no significant dark matter halo around the Milky Way, because otherwise we cannot understand the orbits of these satellite galaxies. Now we can do a second test. We can look at the bar speeds, which one has measured now. So here we have a beautiful image of a galaxy with a huge bar. Now we know that these bars rotate like solid rods. Okay, so this end of the bar must be at the speed of the rotation curve of the galaxy, and then we have a solid body rotation. And so the length of the bar tells us how fast the bar is rotating. Okay, so we have then that the bar is rotating, and it generates a wake in the dark matter halo of the host galaxy behind it, just like with the previous example, and that actually slows down the rotation of the bar. And so if dark matter halos exist, then bars must slow down. The bar rotates like a rigid body, and so the length is a measure of its rotation speed. For a long bar, so this is the distance from the center of the galaxy, that's the speed of the rotation. This is the rotation curve of that galaxy, and if the bar is long, it extends to a large distance to the point where it's co-rotating with the rest of the disk. If it's short, it only extends to a short point, and it rotates much slower. So one can measure that by defining this parameter, which is the ratio between the co-rotation distance and the bar length. Slow bars are if this is large, fast bars are if this is small, because this is a long bar, so this R becomes small. And these are the tests which have been done by Roshan Ghafourian in Iran, in a very, very important research paper. And here one sees the dispersion of this R value in the observational data, and that's the actual R parameter. And you can see that all the data of the observed galaxies cluster well below 1.4, so we have fast bars. The theoretical models, which are in this case the Eagle cosmological simulations, all have very, very slow bars, you see. And in fact, this difference between these models and the data is a tension of more than 8 sigma, which is a radical falsification of the dark matter model. So again, this test by itself now actually very strongly, like completely convincingly, excludes the possibility that there is dark matter around these galaxies which have bars. So we can do a third test. There's the compact groups of galaxies, which we've looked at. So we have the nearby system. It's about 5 million parsecs away from us. It's M81 with these fairly major galaxies around it. So this is like a Milky Way. These are small, like M33, I guess. And you can see that they've all been interacting. There's a lot of gas spread out around the system. That's the scale of 100 kiloparsecs up here. And so we know that all these galaxies have been orbiting at least a few times around each other. Now, the merging of such a system is very rapid. If you have to imagine this galaxy has a huge dark matter halo around it, so does this one, and so does this one, which means that all these dark matter halos are on top of each other, so to be speaking. And so we've looked at this in these research papers, and we find that all members of this M81 group would have to have fallen in synchronously from large distances and have a perigalactic encounter with M81 at nearly the same time without having merged yet. And this coincidence of all these galaxies coming together basically at the same time, just before they all merge, is arbitrarily unlikely. Yeah, that basically shouldn't be happening. And so then just to make this problem worse, we have quite a few of these compact groups of galaxies, which is a problem because they should be merging within 1 to 3 billion years, and then they would make an elliptical galaxy. And so this again shows or indicates very strongly that these dark matter, there's no evidence for the dark matter halos. In fact, these observed systems do not allow the dark matter halos to be there because they are just not behaving the way they should be if they were dark matter. And so if dark matter does not exist, remember the statement, if it doesn't exist, then the whole standard model of cosmology is kaput. So the question is, I've shown you all these tests already, which are all independent of each other. But then if that whole model is truly not correct, as this then implies, the whole model is, it doesn't function, has to be removed, is not a valid representation of the real universe at all, then it would be surprising if it works in other cases, right? So it can, of course, maybe apply and maybe it can explain some observational feature, but it would actually then be likely to fail on all sorts of other independent tests which do not rely on Chandrasekhar dynamical friction. And so if dark matter does exist, are there other signs of failure of this model? It would be, for example, possible that the tests I've just shown indicate dark matter not to be there, but all the other tests show that the model works wonderfully, and then we would have to go back and test whether we've made some calculation errors concerning the dark matter, concerning the Chandrasekhar dynamical friction test. Okay, so this is a check on the tests basically. Okay, so we have this corroborative result 1. Which actually shows us that there is it's based on this KBC void. So when we count galaxies going away from our galaxy, we see that out to a distance of some 400, 500 megaparsec, the number density of galaxies per unit volume is increasing in whichever direction you look. And so this indicates or actually shows that we are living in a huge, gigantic underdensity in the universe by a factor of maybe half, maybe a third or so. Now, such a huge underdensity on a scale of a gigaparsec falsifies the standard model of cosmology with more than 5 sigma, which only allows, which is basically perfectly homogeneous and isotropic on those scales. It doesn't allow for such huge density contrasts on that scale. It allows for voids, but on much, much smaller scales. Okay, so the observed gigaparsec scale KBC void is consistent, however, with MOND. Now, the reason for this is that MOND is effectively a stronger gravity. I'll come to that a bit later. And it allows these density contrasts to grow sufficiently quickly in the current age of the universe to account for this actual void. But the standard model of cosmology based on dark matter absolutely does not. And that's why this is a more than 5 sigma falsification, which is a death sentence for the theory in any physical standard decision criteria. And so furthermore, what is remarkable is that when we take the void and we are in the void and we look at the galaxies as they are receding from us from the Hubble void, they appear to be going away from us faster than the general expansion of the universe, because these galaxies are falling towards the sides of the void. They're being attracted towards the sides of the void just by gravitation, like the apple falling down from a tree. And so this observed void automatically explains the Hubble tension. The Hubble tension doesn't actually exist. It's only a consequence of assuming the universe is homogeneous. Then we locally see an abnormal faster expansion speed. But if we live in this underdensity, then the observed behavior of the galaxies in terms of the Hubble flow is exactly correct. Okay, so there is no Hubble tension in truth because of this void. And this was published in this research paper led by Hasselbauer and Indranil Barnik. Here are their images. And then there's corroborative result number 2. We observe an massive ElGordo galaxy cluster, which is actually interacting. The two 10 to the 15 solar mass galaxy clusters have passed through each other. It's a bit similar to the bullet cluster, however, at a redshift of 0.87. And this falsifies the standard model of cosmology with more than 5 sigma confidence, because the universe is not old enough at this redshift to grow such huge galaxy clusters. It can't do it by just the Newtonian gravity and the dark matter. And so this is yet again a falsification of the model at that significance. But again, in a Mond cosmology, because of the effectively larger gravity, these huge structures can form sufficiently rapidly, and it's this cluster at that redshift is perfectly consistent with a Mond cosmology. Okay, and this was published in this research paper in 2021, led by Elena Asensio. And again in the Albanic. And then we have corroborative result number 3, which is a recent result, and that is really quite an interesting situation. I've told you that most galaxies out there are very, very thin disk galaxies, razor thin disk galaxies. So the Milky Way has a thickness of the disk of about 700 parsecs, and a total diameter of about 30 kiloparsecs, which means it's a razor thin disk. Okay, and one can now test for the observed sky projected thicknesses of the galaxies, take into account the fact that you don't see them all edge on but actually inclined, compared to the predictions or calculations from the standard model of cosmology, and one finds that the galaxies that form in the standard model of cosmology are far too thick, and that's very trivial to understand. That's because the galaxies are bombarded by all these dark matter subhalos and dwarf galaxies in the merging process, and it's impossible to grow these very, very extended, very thin disks and keep them. And so our Milky Way thin disk, for example, has an age of 10 billion years, which means it couldn't have had a merger since 10 billion years. But over the last 10 billion years, most of the mass of the galaxy was assembled. So how do you assemble the mass of the Milky Way without merging? Because that's the way galaxies grow in this model. And so again, this fact that the galaxies are razor thin disks is consistent with Mond cosmology. And so this was published in this APJ paper in 2022, again by Maurice Hasselbauer and Indran Elbanik. Then there is another corroborative result, which is result number 4, which I want to mention here. And that is that the nearest major galaxies have planes of satellites or disks of satellites. And so what we see is that the Milky Way has satellite galaxies which are orbiting, but the satellites are in a plane. It's which is quite thin, and it's rotating. Okay, it's a nearly right angle. It's huge, a radius of 250 kiloparsecs. Remember, the maximum radius of the Milky Way is something like 20 kiloparsecs or so. This is 10 times bigger and nearly perpendicular to the galactic disk. And then you look at Andromeda, it has an even stronger structure, even thinner disk of satellites, which is directed exactly at the Milky Way. And then Centaurus A, which is one of the nearest host galaxies, has another extremely well quantified disks of satellites, which is actually rotating around Centaurus A on this huge scale. And so the fact that there are these 3 just right next to us, basically, falsifies the standard model of cosmology at, again, more than 5 sigma confidence, because while in the standard model of cosmology there is a certain very, very small chance of getting a disk of satellite galaxies which are forming a disk-like structure which is rotating, to have 3 of these extremely pronounced planes of satellite systems is a falsification which is more than 5 sigma confidence. Okay, again, it's consistent with Mond cosmology. That's not my fault that it is, but that's just the way it is, because in Mond, when galaxies interact, they pull out tidal arms in which new galaxies can form. They later orbit in a plane, and that's most likely the reason why we have these disks of satellites, because of past strong encounters, but not mergers, not necessarily mergers. And so this was published very nicely in Nature Astronomy by Marcel Pawlowski, and that's a very nice paper to look at on this topic. And so every test performed actually falsifies the standard model of cosmology. That's again not my fault. It's I think the hypothesis that dark matter exists is very reasonable, a very sound hypothesis, but it's just not what the universe is doing. So the standard of cosmology by now is the most ever totally falsified, but believed to be correct model in the history of science. Okay, this is a very unique situation which we have in the natural sciences, which has never been there before in history ever. This is, of course, somewhat worrying, and this actually started in 2010 when I myself got convinced that, I was leading a research paper, that there is a big problem with the SMoC, and then it just continued here up until today, where it is now completely falsified. However, everybody immediately always says, but the cosmic microwave background, only the lambda CDM model can make it. Yeah, and that's always the very strong argument to say, yes, I know all these tensions, they are there, but the CMB is what actually tells us there is dark matter and only this model works. Would be nice if it were like that. On uniqueness, this is now an issue of how does the scientific process actually work. So the standard model of cosmology reproduces the cosmic microwave backgrounds. That is true. It's a true statement. And you can see here the power spectrum of the cosmic microwave background on the sky. So these tiny little temperature fluctuations and the way they correlate on the sky. There's a lot of power in this peak and the other peaks, and it's a perfect match. The lambda CDM model is a really perfect match to these data. So this is a standard argument for the existence of dark matter and for the truth of the LCDM, LW, so just dark matter models, because of the ratio of these peaks. That tells us very strongly, there's a very strong constraint on the amount of dark matter which has to exist in this universe. And so there are, however, some anomalies I want to mention for fairness. I refer the audience to look at this paper by Schwarz et al., published in 2016, who discuss the not so perfect aspects of this fit, which is very interesting because these type of anomalies are indicating potentially new or yet hitherto not understood physics. So concerning uniqueness, it's true that the standard model of cosmology reproduces the CMB, but, and this is now what we have to take account of, a given observation can be fit by any number of theories. I think that's a correct statement. So for example, you look around yourself, you see a flat horizon, and that flat horizon, that observation, can be fit by a various number of hypotheses. It can be fit by a flat Earth hypothesis. It can be fit by an egg-shaped Earth or by a round Earth model. However, all the models except the round Earth model are falsified by observation. Example 2, okay, the observation of the sun's motion around us. So you sit on your Earth and you see the sun passing overhead. And that observation can be fit by a geocentric, a heliocentric, and even a galactocentric model. And again, all the models, apart from the galactocentric one, are falsified by observation. So the fact that the geocentric model accounts for the motion of the sun does not mean that it's correct. Okay, it's falsified by other observations, and so it's simply not relevant anymore. So concerning the uniqueness issue, so the CMB is reproduced by the currently standard dark matter models. It's also reproduced by the Angus 2009 new HDM model, which is actually a Mond cosmological model. It's also reproduced by the Skouras-Sloznik Mond relativistic formulation from 2019. It's also reproduced by the Skouras-Sloznik 2021 Mond relativistic formulation. And this is just an example here from this paper by Skouras and Sloznik, published in 2021. With this title here, you can see the data, and that model, which is these three curves here, is a perfect representation of the CMB, and it's a Mond model. It has no dark matter in it whatsoever. And furthermore, perhaps the CMB is also explainable by a dust-enshrouded universe. This is a paper by Wawrzyk, published in 2018. The idea here is that the first stars which formed churned out huge quantities of dust, making the universe opaque, but that dust is radiating in the infrared, and we might be seeing it as the CMB today. I put question marks here because this is not so clear now. So the current standard model of cosmology, it reproduces the CMB, but it is falsified by observation. So it is not a relevant model, even though it reproduces the CMB. And so what are the implications of this? Remember that there were many such searches for dark matter since the 1980s. Okay, and nothing has been found, plus the existence of dark matter is falsified by astronomical observations, by all those tests I mentioned, in particular the Chandrasekhar dynamical friction test. And so the only possible logical implication from this, which a modern scientist should really take, is to stop searching for dark matter. I mean, there's no point in searching for something which simply isn't there, and it's actually falsified, and to study models without dark matter. I mean, that's what a scientist really has to do, right? So instead, what's happening actually is, and this comes from nearly a year ago, the search for dark matter is actually dramatically expanding. Okay, so that's something where, well, this paper or this contribution here by Charlie Wood is very nice. Okay, so it really shows you a very nice overview of all the dark matter particle models or ideas which are being brought up. For example, here there's ultralight dark matter in this regime, then there's axions here, and there's sub-giga electron volt dark matter, and these are these weakly interacting massive particles in this regime, and there could be even primordial black holes. And so there are all these searches which are named here, for example, Xenon T and so on, Sensei, which are looking for these various possibilities. Now, it would be okay to maybe continue the searches if the existence of dark matter hadn't been falsified by Chandrasekhar dynamical friction, but I do not think it is correct today anymore to expend further taxpayers' money on these searches. Sorry to say that so bluntly, but I really do think that is now starting to be not correct behavior anymore by the scientists. And so Catherine Zurek from Caltech says, if current WIMP experiments don't see anything, then I think there's going to be a substantial part of the field that's going to shift into these new kinds of experiments. I mean, as a taxpayer, I would simply go on a barricade here, honestly. So has the scientific method ceased to be valid? Has falsification been falsified? Does it not count anymore that one can actually falsify a hypothesis? You just keep on searching for something which you believe is there. Are the scientists following merely their beliefs? Have scientists mutated to ancient Egyptian priests? The priest who contends for a river god is getting donations from the population because he can speak to that river god, right? So dark matter does not exist. That is now a completely clear situation. And thus we need to modernize gravitational theory and revise the cosmological model. And that's the way forward. And so the historical context, we know that gravitation is actually not understood. So is it a consequence of space-time curvature by Einstein and now by this remarkable work by Skårdet and Zloznik in Prague? Is it a consequence of differences in spatial information content, as suggested by Verlinde, very interesting ideas and published? Or is it simply the consequence of the wave nature of matter, as published in this research paper or suggested by this paper? Now, what we understand about gravitation so far is that it has been formulated from observations, an empirically derived law. Okay, it goes back to Newton 1687 and Einstein 1916, which is just a different formulation, more powerful formulation of these ideas, but only using solar system data. At the time of Einstein, galaxies were not understood to be what they are. And so it is today applied as an extrapolation by more than 9 orders of magnitude. So this empirical work and this formulation, even Einstein's, is today extrapolated by 9 orders of magnitude to the scales of galaxies and the whole universe. And so, of course, it's no wonder that it fails. It fails, and so one hypothesis is maybe it's valid and we need to add dark matter. That has been falsified rigorously now. And so the other possibility is to actually amend the gravitational law. And that's what Milgrom did. He looked at the galaxy data and actually revised what we know about gravitation and formulated a new theory of gravitation. And what he did is he was motivated by the flatness of a few bright galaxy rotation curves which were known prior to 1983. This is analogous to Newton being motivated by the falling apple and the moon's motion to write down his theory of gravitation. Okay, this is a motivation. Given this motivation and what is published in 1983, one predicted what the rotation curves of dwarf galaxies and low surface brightest galaxies should look like, which were not known at this time in 1983. They were discovered much later, actually by Stacy McGough. And these rotation curves, the predictions from this theory are perfectly essentially verified by these data. Now, a verification is not a proof of the theory. It just means that this theory passes this test. We have a Lagrangian formulation, which goes back from Bekenstein and Milgrom, 1984, and another one by Milgrom, 2010. So we have a Milgromian Poisson equation, which means we can calculate the potential sourced by a baronic matter distribution in a computer. And so what is this MOND? Is it a new symmetry, space-time scale invariance? It's a deviation. It is definitely a deviation from Newtonian dynamics, Einstein's GR. Is that due to the quantum vacuum? And there's a very nice analogy which goes back to Indra Albanic, and that is as follows. You look at a trampoline and you put a weight into the trampoline and measure how deep the trampoline extends. So make a graph like this. This is the depth of the extension downwards of the trampoline versus the weight. So if you put 100-gram weight on this trampoline, there will be a certain depth. If you put a 10 gram and 1 gram weight, the depth will be smaller. So this is now our law. We formulate that as a line. That's the law of dynamics in this situation, and we can extrapolate it. Will this extrapolation work? Well, obviously not, because there will be deviations at some point because molecular forces start playing a significant role below a certain critical weight, very, very small weight one puts in there. It will simply not react anymore like in the more massive regime here. Okay, and that's basically what we are seeing in nature. If you can interpret space-time as being curved or distorted, then that's a nice analogy. So we have here the observed acceleration versus the acceleration which one should see if Newtonian gravitation were correct. So for the solar system, we have these planets which are exactly on the one-to-one relation. The observed force acceleration towards the sun is exactly what the theory tells us it should be. So that's where the gravitational law was actually derived here, 1687, and in 1916 Einstein still only had these data to constrain his theory. And then later on astronomers applied the same theory to an extrapolation by orders of magnitude, 10 orders of magnitude, and now they find these deviations since the 1980s, deviations in this very, very small regime. So this is the Newtonian regime. This is the Milgromian Mond deviation here, and you can see the small scatter. And that deviation at that point actually gives us Milgrom's constant, which is apparently, it seems, a new constant of nature, which has these values. And so I'm stopping here because the time has largely passed, and I just want to mention that research is continuing on Mond cosmology now. We are particularly in Bonn and Prague, so just let me show this quick movie here. These are the first cosmological simulations in Mond with external field effect, without with external field effect, without. You can see that filaments form, voids form, and galaxies form in here. And so we are now studying the properties of these galaxies in this cosmology paper, which is just about to be submitted. Niels Wittenburg's the first author. You can see how the external field suppresses formation versus no external field, where we get more massive galaxies. And with that, I want to end, leaving you with these directions to recent major reviews by Fermi and McGough, Barnick and Zhao, a very nice review here. And then this amazing book by Merritt, A Philosophical Approach to Mond, which actually is an award-winning book published by Cambridge University Press. So thank you, and yeah. if there are questions, I'm happy to take questions.
Oh my goodness, that's a lot to digest. Thank you so much for the presentation. It was wonderful. Very, very, very interesting. There might be a slight delay between our meeting and the live stream, and some people might have gone back a bit to rewatch something. So I'm just going to start off with some basic questions.
Sure.
Well, yeah, sorry, I had some questions about dark matter, but I guess you falsified dark matter, I guess, halfway through your presentation. So,
well, my apologies. My apologies. You know, it's yeah.
No worries. Yeah, I was going to say, what's your favorite dark matter candidate, but I don't think that will make sense right now. So I will start off with a different question, maybe. I get confused sometimes, or maybe other people get confused, the difference between dark matter and dark energy. And from what I understood, dark energy was more about the expansion of the universe.
Yes.
But,
right. Well, maybe I can put in the following terms. So, assuming this standard model of cosmology, let me just go quickly up here just to put these basic assumptions on here again. So assuming the standard model of cosmology, these assumptions, we now have that the universe is expanding after the Big Bang, and because of the self-gravity of the matter, of the energy density, of the energy content of the universe, it's slowing down the expansion, right? And so we have now had these tests of this expansion rate using supernova 1A standard candles, and those tell us that the universe is expanding more rapidly than it should be because of the slowdown. And so it seems that the universe has been slowing down, and now the only way to fix that mismatch is to put in some method of actually pulling it apart again. And the way mathematically to do that is to basically have another inflation period. That's called driven by dark energy. It's something which one can input into these field equations to tear it apart. Now then, sort of maybe philosophically less nice aspects of this is that the universe would then be torn apart completely, right? Just completely be torn apart. So the dark energy is something which is not at all understood. And dark matter, as you can see, already has issues in the sense that there's no clear prediction of what the dark matter particle should be, because otherwise would have been able to falsify it just by finding that it's not there. It's just thought that something is there, hasn't been found. It's actually been falsified, as I was explaining. But dark energy, at least that is still something which would be gravitating, more understandable in the sense of it would be obeying the dynamics we understand from normal matter, is the gravitational dynamics. But dark energy is now completely not understood. Now, I wouldn't want to claim that I'm the biggest expert, but I recall that there's a very large difference between the vacuum energy density one requires from quantum field theory and what one would associate with this dark energy by something like 100 orders of magnitude, which is a total mess up of understood physics. And what this dark energy would be, it's supposed some vacuum dark energy with a very peculiar equation of state so that it's repulsive. Yeah, that's what I would maybe say to dark energy. And I would maybe say the following, and that is that the problem the way I'm approaching this whole situation is to say that the pillar of the standard model of cosmology, which is dark matter, is falsified by observation. Therefore, to ask the question whether dark energy exists or is real is then simply irrelevant because the whole model collapses. We can ask the question once we have a new model which is not based on dark matter. And if that also requires some sort of dark energy, then it's up on the stakes again. But at the moment, it's pure speculation, yeah, and not even relevant really for the real universe, given the fact that the main pillar, that means dark matter, is simply not there. So I hope that's adequately reacted to your question.
Sounds good. Vilga is asking a question I had in mind too. He asks, how does Mond explain the bullet cluster results?
Right. Yeah. Okay. So the bullet cluster is a problem for the standard model of cosmology. I mean, I know it's always said that it proves dark matter and it actually kills Mond. That is actually incorrect. It is truly a wrong statement. Now, I've mentioned the ElGordo cluster. The ElGordo cluster is very massive at a fairly high redshift, and it couldn't exist at that redshift. It's simply too massive for the standard model of cosmology. Now, the bullet cluster is less massive, and it's at a smaller redshift, so it's nearer to us. The universe had more time to build the bullet cluster, and the bullet cluster is marginally consistent with the standard model of cosmology. So it could have grown such regions, associate neighboring regions of space, grew these clusters, and there's nearly enough time for the clusters to have accelerated towards each other, penetrated each other, and that's where we see them today. Okay, it's marginal. It's sort of not really easy to do in the standard model of cosmology, but it's not something where one can say that really falsifies the standard model of cosmology. So now in Mond, it's very easy to form such clusters. Okay, there would be quite a few bullet clusters out there because the universe is able to make such clusters which have enough time to actually penetrate each other. The problem which has been where the community has been arguing that the bullet cluster falsifies Mond is because the weak lensing signature around the bullet cluster tells us that the mass is in the clusters which have penetrated each other, but the gas is in between. It got stuck in the collision, right? And so this shows that the dominant amount of mass in the clusters must be collisionless. So it's just like dark matter particles just passes through each other with some dissipation through the dynamical friction. But of course, in this case, you have similar mass objects. And so in Mond, the bullet cluster is missing something like a factor of 2 in mass, not a factor of, I don't know how much it is, 10 or 100 in standard model of cosmology, where you have the dark matter halo. So in Mond, you can do everything, except that the weak lensing signature, as has been published, would still demand there to be some additional mass in these bullet clusters, in both of the clusters. And that mass accounts for something like a factor of 2 more than is in the gas and the stars and galaxies. And that additional mass is not really a problem for Mond, because it could be cold gas, which has simply not been seen, and that's the case for every galaxy cluster. It could also be sterile neutrinos, which which are proposed to exist just based on standard particle physics arguments. So one can, without even looking at galaxy clusters cosmology and looking at the physics of neutrinos, and again, I'm not an expert, I'd have to read up on this myself, but I know that from just looking at the physics of the neutrinos, one can argue that there is likely to be another fourth neutrino, which is called the sterile neutrino, which has its properties, that's why it's called sterile, and that mass can be something like 10, 11 electron volts. That's perfectly possible. And if that sterile neutrino is there in the quantities which just that argument tells us, assuming Big Bang nucleosynthesis, we can calculate the number of neutrinos which would be there, then that is exactly the amount you need to make the lensing signature in the bullet cluster around other galaxy clusters. And that's the new HDM model, which Gary Angus has formulated in 2009, where the idea is that the universe evolves according to Mond cosmology, but there are the sterile neutrinos, which then add gravitating mass on the scales of galaxy clusters, but only about a factor of 2, so it's a fairly small amount. And on the scales of galaxies, they don't play a role. So the bullet cluster is fine with Mond. It's less fine with the standard model of cosmology because of the problems, the universe not being really old enough to make such clusters.
Well, that's a very detailed answer, thank you. But I hear bullet cluster mentioned all the time when they're talking about dark matter, the
Sure.
existence of it.
Yeah.
You mentioned sterile neutrinos, which I looked up a bit from their presentation in November. It seems very interesting, and it would make sense. I mean, because you only see one chirality of neutrino, but then I guess this sterile neutrino would have the other chiralities, and then you would have the CP wouldn't be violated, the charge parity. But from what I understand, if I remember correctly, even the most exhaustive searches for this haven't been inclusive yet.
Absolutely.
Yeah,
That's correct. So it's possible that the stellar neutrinos, there's sort of a similar problem to the dark matter searches. One doesn't really know what is looking for. One can exclude parameter space. But you know, if you have so galaxy cluster is made up mostly of a very massive plasma ball. It's a plasma ball in which a few galaxies are orbiting, right? Most of the mass is in the gas. Now, that gas is radiating X-rays, so it's cooling. Now, the question is, where's this cooling gas going, and what is actually heating this whole few megaparsec huge plasma bubble in space? And those are, as far as I know, not completely understood issues. So that's an interesting problem to try to make some advances on. But the point is that since all this gas is actually cooling all the time, it must be cooling to some structures which perhaps are not observable, and maybe that is an alternative explanation for what looks like collisionless dark matter, so colder clouds of gas which condense out of this cooling flow or hot X-ray emitting gas, and then it evaporates again because it's simply because of all the radiation in that environment. I don't know, but I think the missing mass in galaxy clusters, which the Mond theory is faced with, is really not very important because it's only a factor of 2, plus it might be just cold gas. But you know, it is also possible that Mond is not the final true answer. That's what actually everybody working on Mond expects. It's just currently a formulation which we can use, we can work with. It's entirely possible that there will be deviations on even larger scales, and maybe that's part of the deviation.
Very interesting. Yeah, so I guess this isn't Mond, but you mentioned Eric Verlinde, or you showed his paper for the entropic gravity.
Yes.
Could you explain a little bit about that? Or I know it's not what you're researching, but
yeah,
yeah.
I'm there. I'm getting on. Let me just see. It's yeah, this one here exactly. So there. I would be on icy ground, or slithering on the ground. I wouldn't claim I've understood it. I've only noted it because it was very much in the media, and it was celebrated as a important advance, which I think it is. It's if I remember correctly, it's based on the ideas of the entropy of black holes, which go back to Bekenstein and even Hawkins. Yeah, Hawkins radiation, Hawkins. So the how much information can you store on the horizon of a black hole, also, which is related to the mass of the black hole and therefore to gravitation. And Verlinde, who's a string theorist, put this together in a very interesting way and is arguing that one can show that from the entropy differences based on the work of Bekenstein and Hawkins, one can derive emergent forces. They are not true forces, they're just apparent forces because nature is trying to, I think, elevate or trying to reduce these entropy differences. So I think that's what I could say to that, but I have not really studied that in much detail. There have been some tests of the theory which have been partially positive, partially negative. And I think it's very difficult to make explicit predictions, a difficult theory to work in, actually, to, you know, how do you put that theory into a computer to do, say, a cosmological simulation? That's the sort of challenge. We can do that with Milgrom because we have a nonlinear Poisson equation. So that took some time to formulate, but now we have a number of computer codes so we can actually solve the equations of motion in the computer and allow the structure formation calculations. And that's not yet at this point not clear how to do this with Verlinde's suggestion. But nevertheless, it's one of the leading contenders at the moment. That's why I've put it here for potentially understanding the true foundations of gravitation, which today I would say is still not really understood. We don't really know what gravitation is.
Right. Yeah. From what I remember, at least the last paper I read about this entropic mass it's still very limited in how it can be applied. And yeah, putting it into a hydrodynamic simulation would be very difficult.
I think so, yeah.
The Milgram-Poisson equations, this was from a paper from Milgram, right?
Say that again, what are you?
The Milgram-Poisson equations, this is like very similar to the Lagrangian equations, right?
Well, Bekenstein and Milgram, 1984, wrote down a generalized Lagrangian for the gravitational part of the system, and they looked at the self-gravity term and generalized that in the most sort of simplest way, but which is more general than the standard way of writing it, and derived a generalized Poisson equation from that, which is nonlinear. So I didn't put that into a slide because I thought I wouldn't want to go into that depth, but it depends on it's a nonlinear function because there's a parameter in there so there's a divergence of the transition function, which is written as mu in the standard way, times the gradient of the Newtonian potential, and the argument of this transition function depends on the potential, so it's nonlinear, and that has to be solved in a computer. There are various methods of doing that now. It depends on the transition function, which is something which is a bit unclear in the Mond framework, although there are observational constraints on the form of this transition function. The historical analogy here would be, as Moti Milgram himself would also say, is that of the black body spectrum. When Planck wrote down his Planck function, the H is a Hilfsgröße, right? Because at that time one didn't know what it was, but you needed to include that parameter in order to have that shape which fits the high energy and the low energy part of the measured black body spectrum, which was not understood by theory at that time. And Planck showed that one can actually reproduce this with this fitting function, introducing this constant H, which later was realized to be actually related to the quantization of energy, right? And so in this case, one again needs this sort of fitting function from the one regime to the other regime, sort of high energy regime, which is the solar system, up down to the very low energy regime, which is the very far away, very low gradient regime, and that transition function is unclear where it comes from. There's no actual theory for that at this point, although Milgram wrote a paper, I think it was in 1999, where he showed that if one considers basically flat space-time and you have an accelerated particle in that, then it sees a blue shifted vacuum. That blue shifted vacuum exerts a radiation pressure on your vacuum, which, however, in flat space-time cancels because you have the Gibbons-Hawkins radiation from the horizon of the whole universe. And so when you are in a region which is very low curvature, your inertial mass increases in the sense that you can accelerate faster or more for a given acceleration. So you actually get a larger effect because the Gibbons-Hawkins radiation from the horizon of the universe cancels out the vacuum effect, but in a more strongly curved regime, this cancellation doesn't happen, and so the particle feels a stronger radiation inhibition basically against its movement from the vacuum. Well, that's a suggestion, and he wrote it down, published, I think it was APJ, and that's probably, it seems to be an extremely important suggestion to consider. It's actually showing that how gravitation might be related to the quantum regime in a very, very novel and interesting way. However, there's been some other papers looking at this, but I myself haven't had time to study this in any detail. And I think the quantum field theorists, they should look at this possibility.
I'm sorry, I get very interested, so I'm asking a lot of questions, but do you have time for one more?
Okay.
maybe. You showed very nicely at the end of your presentation there was a hydrodynamic, or there was a cosmological simulation, including MOND. Very interesting. You also mentioned that a lot of people still support this dark matter theory. I was wondering if any of these cosmological simulations have included or tried to investigate the Chandrasekhar dynamical friction.
Well, so that's automatically within those calculations, because in the standard model of cosmology structure formations, which look quite similar to what you're seeing here. So if you look at a galaxy like let's look at this galaxy here. So in those simulations, you would have also filaments and galaxies which form in the filaments, and they would have the dark matter halos around them, right? And so in those simulations, when a dwarf galaxy like this one here, a smaller galaxy, enters the dark matter halo of this larger one, it would automatically suffer Chandrasekhar dynamical friction, because in those calculations, the dynamics is correctly calculated. All the gravitational forces between these particles and the galaxies are correctly accounted for. And so these galaxies suffer dynamical friction in those simulations, and they merge. And so in those simulations, there's a lot of merging. The galaxies all form largely through galaxies which fall in and then merge because of the Chandrasekhar dynamical friction. And in these simulations, that's not happening. So there's no dark matter halo. And so this galaxy would pass this galaxy and just keep orbiting about it. Yeah, that's basically the difference here. In these simulations, the galaxies only grow through initial collapse of gas clouds and then accretion of gas. And we are now currently actively investigating exactly this process. So Niels Wittenberg is now preparing a second publication where we are looking at how these galaxies are growing just through the accretion of gas, and how consistent is that with the observed galaxies. So, one shouldn't understand me wrongly that I'm saying dark matter doesn't exist. This, I'm completely confident about that. But I wouldn't say that now, because dark matter doesn't exist, this is the only truth, right? We are now attacking this type of model exactly with the same harshness, you could say, as the dark matter models. We want to see where it fails, and so far we haven't been able to uncover any real serious 5 sigma failures.
Oh, very interesting. Thank you very much for the presentation. And I hope everybody learned something about dark matter. And I did, not dark matter, but MOND, or why dark matter fails certain tests. So thank you very much for this.
Yeah, pleasure, and thank you for having me.
I go now to present some recent news. So you are welcome to stay for this, or if you have to go, I understand.
I'll stay, but I'll turn off the camera for...
Sure.
Yeah, okay.
Sounds good. So here is the Astro News, at least what we have so far. With a 3-month hiatus, lots of things happened in the 3 months, but I don't want to dwell on things that happened so long ago. As everybody probably knows, James Webb Space Telescope was finally launched on December 25th. It made its 1-month trek to the L2, the second Lagrangian point. It finally received first light last month, or earlier, 1 month ago, exactly. But this, when it reached L2, and then it had to unfold because it has its reflecting mirrors, and it has a camera that's hoisted in front and collecting all of the light. It had to align all of these and make sure that this can make very precise images. So this was part of the joke when it was first launched and it was first looking at objects on the 3rd of February. Amateur astronomers were joking that they could make images that were clearer than James Webb Space Telescope. But now it's starting to get more realigned. And so now this is the first image with full alignment. It's not complete yet. There's still some improvements that they need to make, but this is the first one with all of the mirrors pointing in the same location at a star, and you can see some other sources here. And what's prominent here are the standard diffraction gratings that's given from the beams that are holding the camera, the sensor. And so this is just a very interesting image that was recently released. What else? There's, yes, when galaxies interact, there's this famous couple of galaxies that have interacted, and they're labeled as peculiar galaxies because they have slightly deformed shapes. What I don't have here is that there should be a bar of hydrogen, neutral hydrogen, that's linking the two to show that they do in fact interact. And then this increases some of the star formation, at least in this larger one, and it deforms the smaller one. Pavel, are you familiar with this pair of galaxies?
Not really, no. This looks very interesting, especially the third one up on the upper right, but I'm not sure if that's connected.
Yes, I'm not sure either. Yeah, they mainly talk about these two, but at least this will be one of the first sources for James Webb.
Sure, that looks like a very interesting target indeed.
Yeah.
But you can see one thing, if you just go back, you see how the disks are perturbed. Yes, sorry to...
sorry, I'm going...
Yeah, so you can see that. So this one galaxy in the middle seems to be quite perturbed and has a fairly thickened disk with stars being scattered everywhere. You can see like this yellow nebula, and that's exactly why observed galaxies. So why galaxies in the dark matter models can't be thin, because if there's one merger, the disks are just messed up.
Yeah.
So that's quite nicely seen here, I think.
Yeah, I really like that. Yeah. Yeah, this would be great for studying galactic evolution. Another result, I think this was from this week. Anyways, from 2020, there was a team that claimed to observe there's a triple system that included a black hole, and this was actually the closest black hole to Earth. And they knew that it was a triple system because they knew it had two sources of light, two stars. But they thought there was one star with 40-day period around the black hole, and then one star in a wider orbit. And so they took higher resolution data with very large space telescope, or very large telescope in Chile. And then they've determined that actually the star that they thought was in a wider orbit was actually in a smaller orbit, and it was actually just a binary system with a 40-day period. But thanks to the high resolution observations, they could confirm this. What was interesting with this is that one star is stripped. So when a star gets too large in the binary system, or at least a close binary system, it starts to donate some of its mass to the other star. This is accretion. We say it accretes onto the other star. But this is what they have observed, is that one of these stars is in fact stripped. For exoplanets, exoplanets are always in the news. They've analyzed this one exoplanet, WASP 121b. They were able to analyze the atmosphere, which isn't very common to do. It's very difficult. We can't usually get the amount of data that they need to do this. But what they were able to do this, they were able to discover water, I think a couple of years ago, in the atmosphere. So this exoplanet they know is about the size of Jupiter, and it's orbiting very close to its host star. And yeah, the period of orbit is just over a day long, 1 Earth day long. And because it's so close to the star, it's actually tidally locked. So much like the moon with Earth, it only one side of the exoplanet faces the star, and then the other side is completely in the dark. That being said, it's still impressively warm, from 1500 degrees Celsius to 2500. 1500 would be on the dark side, 2500 on the day side. Because it's so hot, it has no water circulation or water network like we have on Earth. But actually, there is a hypothesis that there's metals that rain down, or liquid metals that rain down on this planet. Because it's so hot, like there's no water clouds or anything like this, so it's all metals and trace elements of metals that are in the clouds that sweep across this planet. And then there's a hypothesis that they detect no aluminum in these clouds, so then the aluminum, they think, would be involved in this cycle that would rain down on the planet. And when aluminum combines with certain other metals, then it can create rubies and sapphires. So it was a bit interesting. Now there's another planet that also gets a lot of sun, but they were able to see an exoplanet that was orbiting around 2 stars. So yeah, when you read the press release, it's talking about Tatooine from Star Wars because it has 2 stars. And so what is unique about this planet, but not necessarily unique, but it's a gas giant. So it's not a terrestrial planet like Earth, but it'd be more like Saturn. And it's about the same size as Saturn, but it's located in the habitable zone of this system. But it is a binary system, so then it receives a lot of sun, and it would have 2 sunsets and very little night. And this was the first exoplanet to be confirmed in a binary system using its radial velocity. So this is how quickly is it moving towards or away from us. And you can tell this from the different molecular lines or transition lines, and how much this is red shifted or blue shifted, and to see if this is moving towards or away from us. But very interesting. Right, so now this is the last point that I wanted to make, or last bit of news. This isn't exactly even new news, because this type of work has been done in the 1960s. So what they are doing is, at the pyramids in Egypt, they use muon topography. So muons are product of certain cosmic rays. Cosmic rays are particles ejected from stars all over the place. And so you have a certain amount of cosmic rays that hit Earth or interact with Earth's atmosphere, the ionosphere, really. And then due to the collisions, these are high energy particles. And from these collisions, they create secondary particles. And then these particles decay and decay, and this is a particle shower. And this is typically how astroparticle physicists observe things. And so a common type of cosmic ray shower to observe would be these muons. And muons are like a heavier type of electron. And so this type of work has been done for the first time in 1969, where they use muons and this muon topography, and they put all these detectors around the pyramid, and they try to detect what is the structure inside the pyramid, because these muons can penetrate through the pyramid, and then they can see different fluctuations based on what they detect. They can determine if there's some room or some chamber in the pyramid that hasn't been discovered yet. Like they can kind of map out the interior of the pyramid. So I remember when this was applied in 2017, and there was a lot of people talking about it discovered a new room. Some people didn't like it. Some of the other researchers didn't think that it added any new information, but it was very nice use of these cosmic rays. And so now there's another group that is going to be setting up these detectors, and they're going to put it on the perimeter of the pyramid, and then they're going to try to detect and analyze these muons. They haven't, there's no physical test that they've made yet. So all of this is just from modeling and simulations, but they're hopeful that they can correctly map out the layout of the pyramid, and if there's any density fluctuations and things like this. So should be interesting. But yeah, that's the news this time. That is all of our event for today. So thank you to everyone who stayed for the entire event. And I hope to see you next time, or at least in the comments. And
Well,
thank you very much, Pavel Kroupa.
Yeah, thank you. It was a nice overview just now also. I enjoyed it. Bye.